All right, so we're going to transition a little bit from radiology imaging to pathology imaging. Our next speaker is Justin Coe, who is an associate clinical professor of dermatology here at Stanford University. He's also the medical director and service chief for medical dermatology. He has started a virtual telehealth program for dermatology, and he's passionate about early cancer detection and has been using AI and machine learning in his research to help bring about that goal. His work was recently published in Nature, and he'll be talking about that a little bit in his next talk called Mountains Out of Moles. Please welcome Justin.
Thanks. Hi, everybody. Good afternoon. I'm really excited to be here and really excited to share with you some of our work that we've been doing with AI and dermatology just over the past couple of years. So no financial disclosures related to anything in this talk. I am a clinician, so you're going to get that clinical bent and perspective. And if you have any questions related to any of the technical details or technical issues after the talk, I'm happy to answer those or talk more about those. I've got one last disclosure here. Let's maybe keep this one between all of us here in the room and I guess all the people live streaming at home. I've got a superpower. That's pretty cool. It's not web throwing or flying or anything like that. It's actually something that makes me pretty popular at cocktail parties, though. I'm able, just with a single glance, to be able to make a diagnosis. And you cannot imagine the number of people who, after I've met for a couple minutes, they're pulling up their shirts and their pant legs and pulling me into the bathroom, I kid you not, to show me their funny moles or their strange rashes. It goes the other way too, actually, the social faux pas. I do it too. So if I'm talking to you, for example, later tonight and I'm staring at your neck, I apologize in advance. I can't turn it off. It just never goes up. A glass of wine sometimes helps, but it never really goes off. But I tell you this because this is actually an ability that it's taken me the better part of a decade or so to acquire, right? But what if we could democratize this ability? What if we could essentially grant anybody the power to wield this just by taking out, this device that we all have in our hands, our smartphone, right? What could we achieve? Just think of what we could do. Could we eradicate death from melanoma because we're diagnosing everybody in the earliest treatable stages? Maybe, right? Could we essentially extend high-quality, low-cost diagnostic abilities to the furthest reaches of the globe? I think the answer to this is yes, and so did my colleagues. So about a couple years ago, Rob Naveau, who's a colleague of mine in dermatology and pathology, sent out an email with this as part of the message, and this was the triggering event that led to a formation of a team focused around this vision of transforming dermatology with AI. So the first thing that we did, and anything that, with this kind of an effort, is build a data set, not just any data set, specifically one that encompassed clinical images across the whole breadth of dermatologic disease. We were talking about clinical images by photograph, but also clinical images of something called dermoscopy, which is a tool that we use as clinicians in the clinical setting. It's a highly specialized, standardized form of images. And altogether, we ended up compiling about 130,000 images. And these are from online repositories, clinician-labeled and many biopsy-proven. And 18 online repositories, open access, in addition to clinical information and data from Stanford dermatology clinics. And altogether, these 130,000 images comprise about more than 2,000 dermatology diseases. And just to give you a little bit of context, this treasure trove that we put together was about 2 times an order of magnitude of twofold more than anybody has ever done before in efforts around machine learning and dermatology. So after we compiled these images, what we did next was we built a taxonomy. We built a tree structure taxonomy. And starting from those individual diseases, we grouped them into broader categories, and we kept on doing that until we completed this structure. And what you'll see here is just a portion of this, but ultimately it's three main nodes here that are essentially the categories of dermatologic disease. We have benign lesions. These are cellular proliferations that cause no harm. We have malignancies, cancerous growth. And then we have things that are non-proliferative. These are largely your inflammatory diseases like psoriasis or acne or eczema. So these are just some examples of images from our malignant category, right? So lots and lots of images. They all look different. Here's some benign images. So we wanted to create a system, one system, that could accommodate the inherent variation in clinical photography, right? You think about all the different angles, the lighting, the zoom, the fuzziness. We wanted to create a system that was able to accommodate that without any pre-image processing, without having to pull out or to have any sort of things that you had to do before it worked. Essentially, we wanted to be able to feed an image, any clinical image of skin, directly into the system and have it output a classification. And so this is what our network looks like. We've got an image here on the left. This one here is of a melanoma. And then using the Google Net Inception v3 architecture, which was trained on the ImageNet database, which then we subsequently trained on our image set data set and then fine-tuned. What that does is that subsequently gives you an output of statistical probabilities for each of these training classes. These training classes are derived essentially from use of a partitioning algorithm applied on top of the taxonomy that we previously created. And then what you do is it gives you probabilities for each inference class. And all this is just a summation of all the individual probabilities of the training classes to get up to that. So this is essentially a map of how our system works. So after we trained it, and then after we did some validation exercises, we were ready for prime time here. This is what we were after. We wanted to get to evaluation and testing. This was the main event. And so we had classes of images that were previously unseen by the neural net and by dermatologists. These were all biopsy proven, and these were scrubbed, and we made sure that there were no issues with these data sets. And we tested our neural network in addition to 25 board certified dermatologists at major academic medical centers across the country. What we did was we would show them an image of a lesion. And the only thing that they had to do is say, hey, is this lesion worth additional inquiry? Essentially, would you biopsy this lesion? So just to give you guys a bit of a sense of what this test was all about, here are some images from the test. Okay. So I'm going to tell you that either the top or the bottom has malignant images here. How many of you guys think that the top half are the malignant images? Okay. How about the bottom half? Yeah, about 50-50, right? This is tough. I just want to show you this because this is, this was not an easy task. I wanted to show you what the neural net and the physicians were up against. So this is the right answer. So it's hard. It's hard. And I'm glad it's hard because that's why I have a job, I suppose. But this is essentially how, examples of the kinds of images that we tested. So how did we do? So these are the results for the neural network here. And what we did to create these receiver operating curves was we would measure the sensitivity and specificity, and then just vary the threshold to create sensitivity specificity pairs that result in this curve. And the area under the curve is kind of like an indication of how good it is. The top value is 1 if you're capturing all the area under the curve. And you can see that the neural net performed really well with areas under the curve of 0.94 to 0.96. Pretty cool. But what's even more interesting is how did the neural nets perform compared to human experts, right? So each dermatologist's performance is a red dot. And so most of them have 20, 25, 21. I think some of the dermatologists got really tired and didn't finish some of the tests. But the average dermatologist is denoted by the green dot, and then the error bar is essentially 1 standard deviation. And you can see for each of these tasks, the neural network outperformed the dermatologist. And let me tell you a little bit about the tasks that we chose. These are all clinically relevant tasks. So the first one was essentially distinguishing keratinocyte carcinomas, which are these basal cell skin cancers and squamous cell skin cancers, the most common type of skin cancer, from benign epidermal growth like a seborrhea keratosis. The second task in the middle is distinguishing melanoma from very safe benign moles. And the third one was that same task, but using those specialized images from that tool called a dermatoscope that we use in the clinical setting. So in each of those three clinically relevant tasks, the neural network did at least as well as the average dermatologist, although there are a few examples of dermatologists who outperform the net. So taking aside the fact that this is a completely artificial, contrived experimental approach, and that to make any sort of judgments about what this does in a prospective real-world setting is silly, this is really remarkable. I was blown away when I saw these results, because essentially what it says is that, with a few weeks of training, we can teach a machine to do something that it takes, a lot of the experts that we tested, decades of training and learning to do. And this is just that first initial point on sort of our linear curve of improvement. This by no means represents the peak of what this neural network can do. It only gets better from here. And what a humbling thought that is, right? I've been spending years and years and years, and this thing can do it in a few weeks. We were proud to present our work to the broader scientific community, but I was actually really tickled when I read Eric's Twitter shout out to us. This was really kind of a cool thing, and really was sort of a validation of the work that we had done. But this is, to be honest, only the beginning. And I just want to close, because Natalie's going to come out here pretty soon again. I want to close by telling you a little bit about one patient that I saw in the clinic last month. Actually, it was April 17th. And this is a patient I saw in clinic, and this was a spot on the shoulder. And this was a spot I was kind of debating in my head over, because I was completely on the fence about this. Something that I said, not quite right, but then when I looked at it with my dermatoscope, I didn't see any features that would suggest to me that this was an early evolving melanoma, but my gut didn't really sit right with my gut. And so I said, okay, this is a perfect time to whip out my iPhone. And I took photos. I took photos from every angle, from different distances, with lighting, without lighting, and I fed it to the neural network. And then, remarkably, regardless of the photo, it was pretty stable in the read. And it was pretty adamant that this was a malignant lesion. So that pushed me to biopsy this. I biopsied that. It's not, the reason why it's not necessarily such an easy thing to biopsy is this is a relatively large spot. It would leave a scar, and if you don't have to do it, it's not necessarily the best thing to do. But I biopsied it, talked to our dermatopathologist, and lo and behold, she said, hey, you know what? This is really fascinating. This was a really early, subtle example of an evolving melanoma. So we caught it at a completely treatable stage. He underwent a wide local excision, and he's not going to suffer any consequences from this. So this was, and this was an example. This was the first example of our AI having clinical impact. And that's why I know the date. It's April 17th, the first time that we made a clinical impact. And I hope it's just the first of many. So I really thank you for all your attention and your thoughts. This is my favorite dermatology cartoon by far. And please feel free to just shoot me a message or find me afterwards if you want to chat further, or if you have any thoughts, suggestions, or ideas. Thank you very much. Appreciate it.